In any physics course, we have certain equations that are given. You can look them up in any physics textbook or website, and the equations of kinematics are included there. We have things like the definition of the average velocity of an object and the definition of the acceleration of an object. But if you look up kinematics equations, you'll also find some much more complicated looking equations. And in this video, I'd like to show you which ones you should focus on, which ones are considered given, and where at least one of them comes from. So imagine that you're given this graph of an object's motion as a function of time. The first thing you always want to do is find out for sure, what is this a graph of? Is it position versus time or velocity versus time? So check your vertical axes there. This is velocity versus time. I don't know what made this graph of velocity versus time, some red cart or an elevator or who knows. But from this graph, I can at least know a little bit about the motion of the object. The object started out moving in a positive direction at a velocity of 1 meter per second, and as time elapsed, the object's velocity became more and more and more positive. So this is an object moving in a positive direction and accelerating to go faster and faster and faster in that positive direction. From this graph, I could determine a lot of information. I can determine the initial velocity just by reading the graph, 1.0 meters per second. I can determine the final velocity by reading the graph over here. The final velocity, at least for the period of time we have, is that the object got up to 4 meters per second. From those two pieces of information, I could determine the average velocity, which is 2.5 meters per second. I'm just averaging the initial and final velocities. I can determine the acceleration. Well, before I even get to that, I can determine the change of velocity, which is v final minus v initial. So 3 meters per second. And that means that's how much this object sped up during the time that we're seeing here. And I can determine from that the acceleration. The acceleration is delta v over delta t, or the slope of our graph, and that's going to come out to 0.6 meters per second per second. Now, if I want to determine the displacement of this object from this graph, I need to take the integral of this graph, which means I need to break it up. So I draw a dotted line in here and break it up into two shapes that I know how to find the area of. This long rectangle here beneath the dotted line, between the dotted line and our horizontal axis here, and then also the area between the dotted line and the red, which is a triangle up here. Please be careful when you're taking an integral. Don't take the area beneath this blue dotted line past your horizontal axis. You only want to go to the axis. You don't want to be counting this space down here. That's not part of the integral. So my total displacement would be the area of the rectangle beneath that dotted line, and that is the base of that rectangle times the height of that rectangle, plus the integral of that triangle shape, the 1/2 base of the triangle times the time of the triangle. I'm sorry, times the height of the triangle. The base of that rectangle is the delta t that elapsed, and the height of this rectangle is v initial. So v initial times delta t is the integral of this rectangle in here. And that is actually how far the object would have been displaced if it started out at its initial velocity and didn't accelerate at all. But this one did, so we also have a plus 1/2. The base of that triangle is delta t, right? That's the base of this triangle is 5 seconds, and times the height, which is from here to here, which is actually delta v. It's the difference between v initial and v final. So that will be my displacement. I want to put in my numbers. The area of the rectangle is the 1 meter per second times the 5 seconds. 1 meter per second is v initial, and 5 seconds is the time elapsed. And then for the triangle, it's 1/2 times the base of the triangle was 5 seconds, times the height of the triangle was 3 meters per second. And so I get a displacement of 5 meters plus 7.5 meters, which is a total displacement of 12.5 meters for whatever this object was. And that's great. But I'd like to take another look at how exactly I did that. This equation is the one that I used on the previous slide. The area of the rectangle, the base of the rectangle times the height of the rectangle, plus 1/2 base of the triangle times height of the triangle. So the area of the rectangle plus the area of the triangle. And I'd like to point out in physics equation format, that turned into this, my v initial times time plus 1/2 delta t times delta v. And one of the things that's useful is to note that I can actually replace delta v with some other symbols. The acceleration of an object is defined as delta v over delta t. So I can rearrange this for delta v. I can solve it for delta v equals the acceleration times delta t. And what I want to do is I actually want to take this delta v in this equation and replace it with something it's equivalent to, which is a times delta t. So the displacement of an object is equal to v initial times delta t plus 1/2 delta t times acceleration times delta t, as long as the acceleration is some constant value. And in this course, we'll just be dealing with objects that have constant accelerations. So algebraically, this delta t and delta t becomes a delta t squared. And this is a given equation. If you go to any textbook or website and look up equations of kinematics, you'll find delta x, displacement, equals v initial in the x direction times delta t plus 1/2 acceleration in the x direction times delta t squared. Occasionally, you'll find websites that use different subscripts or textbooks that leave out the delta for the t. That happens a lot. But if you find this equation in any other resource, you'll find just variations of it meaning the exact same thing as what I have written here. And that takes me to why you would want to do that. The reason you would want to do that is that this equation is really useful if you know that you're looking for the relationship between the displacement of an object, its initial velocity, its acceleration, and the time it's in motion. So you don't know v final, but you also weren't asked about v final. The information that's missing from the problem, that's not asked for and not given, is actually our best clue to what equation is going to be the most straightforward for helping us solve the relationship. These 5 equations are on our equation sheet, although at least one of them doesn't look like this on our equation sheet, and I'll explain that in a second. This slide is really helpful for helping you figure out which equation you want to use in a given problem. So this first equation is for when you are missing delta x, meaning it wasn't given, but it also wasn't asked for. It's missing from the equation, or from the question entirely. I do want to point out delta v is v final minus v initial, so a lot of times the problem is worded something like this. The acceleration of an object is 5 meters per second squared. If the object's initial velocity is minus 4 meters per second and its final velocity is minus 2 meters per second, what is the amount of time elapsed? In that question, it doesn't give you delta t, but it gives you v final. I'm sorry, it doesn't give you delta v, but it does give you v final and v initial. So this is the equation that you would then use. You would say, I was given an acceleration of v final, of v initial, and I was asked for delta t. Displacement wasn't given, wasn't asked for. This is my equation. The second equation, it's the one we just derived on the previous slide. It's for when you are not asked about and not given the final velocity. The third equation, I'm not going to derive it here. If you'd like to see it, just pop into the WebEx and ask me, but it is time independent. It's the one that if the question doesn't give you the amount of time elapsed and it doesn't ask about the amount of time, that's the equation you want. The fourth one is actually the one equation that's not on the equation sheet, but delta x over delta t is on the equation sheet as equaling v average, and v final plus v initial over 2 is on the equation sheet as equaling v average. So if you take the two equations that are on the equation sheet for v average and set them equal to each other, you actually get this equation. And again, it's useful if the object is accelerating, but you don't know the value of the acceleration and you're not asked for the value of the acceleration. You're just relating the displacement to time, the initial and final velocity. And then that fifth equation down there is almost exactly the same as the second one. It's for when you don't care about the initial. Don't care about it meaning you weren't given it and you weren't asked about it. That's it for this video, and in the next one we will talk about a special kind of acceleration.